A conservative force is one that can be described internal to a system by a potential energy function. That's a kind of definition that's common in textbooks for a conservative force. Another version of that definition is a conservative force is one that is derivable from a potential energy function. But that might seem a little bit circular because the definition I gave for potential energy earlier kind of referenced a conservative force. And in that sense, I think when I defined potential energy based on force, you could say, well, that's kind of like saying, well, what is a potential energy function? It's equal to the work that you have to do against a conservative force to transfer energy into a system that's going to be stored in that potential energy. In that sense, the concept that I've kind of suggested is that potential energy, all potential energy forms, can be thought of sort of like a battery. And it turns out, actually in a battery, the energy is stored in the form of chemical energy, which is an example of a potential energy. So it should maybe make the list, although exactly what the forces are there, I didn't include in my list of conservative versus non-conservative forces I've put on the whiteboard here because it gets a little bit more complicated, I think, with batteries and chemical forces. I've also made a statement here that says work done by a conservative force only depends on initial and final positions. It turns out that this is another mathematical definition, or maybe it's a property. Sometimes it's a definition, but it's a property that follows from the statement that a conservative force is derivable from a potential energy function. But to state exactly, really to prove this, and to state why this really is so, maybe involves some more calculus than I'd like to discuss here. But it does make sense, right? Like if you think about how much energy is stored in a battery, it should only depend on whatever configuration is internal to it right now, which I'm going to kind of equate to whatever its position is. And in that sense, if I say, hey, this position represents an amount of energy stored, and then I look at moving from, say, one position to another position, how much work is done by a force as those position changes happen. If it's a conservative force, and that is really representing a change in amount of energy stored, or could be represented that way from a certain point of view, then it would have to be that the work done only depends on where you started and where you wound up. Not like how fast you got there, or whether it was like a faster discharge to begin with and then slower, or the opposite of that, or whether it was a relatively steady discharge in the sense of a battery. It really only matters where you wind up, right? So in that sense, this property can also be tied to that overall concept. But to simplify things a little bit more, because there's some really deep mathematical concepts behind really potential energy and the concept of conservative forces, and some of them go a bit beyond really the physics 2A level. There's a lot of like calculus, not just calculus, but a lot of vector analysis, vector calculus involved with that, and that's just stuff that we're not going to discuss all of. We might scratch the surface a little bit. So to keep things a little bit simpler, I have again this list here. Conservative forces in our class include gravity and elastic forces. And, I made the analogy to a battery. Well, if you lift something up, that represents a possible amount of energy stored there, because if you drop it, when it falls down, that energy is converted back into kinetic energy and could be used to also like do work on something instead of just dropping and like landing on my foot or something. What if I use it to power some machine, right? Just like a battery would. In fact, if you look at things like a cuckoo clock or grandfather clocks, they have masses in them that really like store energy and have the function of a battery, but in a more mechanical type of sense. And as they go down, gravitational potential energy is doing work, or is going into work, or that drives the clock. Similarly, with like a wind-up toy, you could say like, some of those involve elastic energy. I've also listed here electrostatic energy just to kind of indicate there's more to the list of conservative forces. I decided to stop there, even though you could definitely keep going with this. You could probably look back at all the possible energy forms under potential energy and associate those here, but I didn't want to go too deep into that. But definitely non-conservative forces include friction and drag forces. Those forces do not have the property that the work done by them depends only on initial and final positions, but it definitely depends on the path taken between them, or how it does that, or even kind of like what direction does it travel as it do that. In that sense, friction, right, points in the opposite direction generally as an object is moving or wants to move, and that can depend on what path it takes. So that's kind of one way of seeing why that can't be a conservative force. But we've also already seen some examples of how it doesn't make sense that when you do work against friction, that can somehow represent some kind of stored energy that can then manifest again as, say, kinetic energy after you stored it, whereas the potential energies forms that we've looked at do have that property, and in that sense it makes sense to define the potential energy function based on that work done against a conservative force.